All right. Yeah. So previously we saw how models can be classified into two categories, parametric and non-parametric. There is another way of looking at these ML models. One is deterministic and non-deterministic. Deterministic means they'll give you the same output every time you run the algorithm. Of course, you have to set the random state for that. And non-deterministic means they may not produce the same result. For example, trees. You change the data, you will get the same entirely different tree structure. Again, examples are linear regression. Now, decision tree is not a deterministic. Okay, linear regression, and it could be logistic regression, etc. And non-deterministic means you have k nearest neighbors and random forest. Again, you change the value of k, the results will change. Next is model behavior is predictable and consistent for deterministic. Non-deterministic is they may vary due to randomness and different initializations that we do. A good example is neural networks. Okay, and next is training process is results are repeatable and reproducible. For deterministic, non-deterministic means results may differ for different runs, and deterministic means use cases. They have high consistency, high reliability, and they are easier to interpret, and they are easier to debug. Whereas non-deterministic means they have model diversity and robustness, very complex, and complex error handling, difficult to fix. Okay, this is just another way of looking at ML models. Next is, see, working with decision trees, we have to understand some of the assumptions. One of the assumption is the data should be recursively partitionable. So that means whatever the data that you provide, okay, it must have certain rules that can be generated. Okay, so data cannot be highly unorganized, highly unstructured. You can't run a decision tree on top of highly unstructured data. Okay, because the decision tree has to recursively partition the data into subsets based on the feature values, and those feature values should follow certain pattern. Okay, that is one assumption. Okay, second is axis parallel splits. Okay, axis parallel splits means for each split, okay, each split is done which is perpendicular to feature axis. So if you plot features into x-axis and y-axis, okay, the splits are done. That's why it's called as piecewise splitting, right? So like this, perpendicular splitting is done. Okay, so that is another assumption. Third one is feature independence. While this is not a strict assumption, so still we expect there should not be any strong correlations between the features. Okay, so if there are strong correlations, trees may not capture the underlying patterns more effectively. So that is another assumption, although it is not a strict one. Next is homogeneity. Homogeneity means decision trees split the data into homogeneous groups, nothing but groups that consist of same data, and the goal is to reduce the impurity, okay, either entropy or Gini impurity, okay, in the subsets. And there should be sufficient data for doing the splitting. And decision tree, while they can handle the missing data, okay, by doing some sort of surrogate splitting, okay, it is still preferable that to improve the model accuracy, we do the missing data handling part. And decision trees assume that the data is noise free. That means there should not be too much overlapping between the data, like what we saw in case of apple tree and oak tree. Okay, data should not coincide with each other. So in that case, decision tree will work very fine. If the data has noises, then we use some techniques like pruning, maximum depth, or ensembling techniques. Next is depth of the tree. So higher the depth, better the performance is what we generally observe, but it will result in overfitting. Hence the depth of the tree should be controlled. Okay, there should be a in order to achieve proper generalization, depth of the tree should be somewhere between 6 to 10, okay, max. And decision tree, decision boundaries. Decision boundary, as you already saw above it, decision trees generate a piecewise constant. This we will see what we exactly mean by this. When you, because at each split lot of data points are taken, at every split lot of data points will show up. That will give a feeling as though there is a piecewise constant. Okay. Next is feature scaling. So decision trees do not assume any feature scaling, hence it is not required. They can handle the features automatically on different scales. So feature scaling is not a concern for decision trees. Okay. Next is when not to use decision trees. When not to use decision trees is if your data exhibits purely linear relationship, then you don't benefit. You can use decision trees, but you don't benefit much from recursive splitting. You could be well off using linear regression or logistic regression. Okay, for example, if you want to predict the house prices, then you can use linear regression. No need to use decision trees. Next is when not to use decision trees, when you have high dimensional sparse data. What is sparse data? Sparse data is when you take the data frame, lot of the values are zeros. Okay, in your data frame, if too many values are zeros, then decision tree, how will it make decision based on the splitting if all the values are, majority of the values are zero, right? So it doesn't make sense. Okay, hence the recursive splitting may not work well. Okay, and this is usually seen on genomic data, something you're working with genomes, okay, or any protein based solutions. Better not to use decision tree. Okay, for example, even text data, if you're using text classification, using, again we'll come to bag of words and IFTDF, okay, TF-IDF, term frequency, inverse document frequency. So in such cases also decision tree is not a good choice. And if you have very small amount of data, recursive splitting may not happen properly. So that is also is not a good data where decision tree can be used. Okay. Next is high structured data. High structured data is where data follows the strict and well-defined rules. For example, I was solving this I was working on one of these use cases very long back, called fraud detection in procure to pay cycle. Procure to pay cycle means if a certain company, let's just say beer manufacturing company, wants to hire raw material, wants to purchase raw materials from various vendors. So to manufacture a beer, you need grapes, you need fermentation products, and you need glass, you need lot of things are required. Okay, raw ingredients are required. So you will have a lot of vendors who will supply you those raw elements, right? Raw materials. Now during that supply, vendors may do some fraud. They may say we have supplied you 100 elements, 100 items, and they may charge for 200. Okay, because everything comes in truck, nobody can count each and every unit one by one, right? That's not possible. Practically not possible. So in that use case, clearly, very, very clearly, you have certain rules. For example, if your purchase order amount increases, okay, your amount paid, invoice amount, it's a fraud. Or purchase purchase order amount is less than invoice amount, the amount that you have paid to them, or they are asking you to pay, that is a fraud. So there clear-cut rules are there. What constitutes a fraud, what not constitutes a fraud, and all. On such data, decision tree is useless. Okay. Data where clear-cut rules are defined, okay, so there decision tree fails. For example, stock forecasting also. Okay, stock forecasting does not follow any trends and patterns. It all depends on how the various companies in the world are performing and what is the human emotion behind those companies, and all of that is there. It's unpredictable. Okay, on that such data also do not follow. that do not follow clear trends and patterns. Okay, so on that data also using a decision tree doesn't make sense, it may not work. Next is periodic data, seasonal data, right? So for example, selling of ice cream, it's seasonal, right? If you have selling of ice cream, obviously you will end up selling more ice cream in when the temperature is high. That is a clear cut pattern right there. On that data decision tree may not work well. Okay, this is again interview questions. They may ask you to list out at least 2 to 3 different scenarios where decision trees may not work. So you have to speak up all these things. Clear? Next is NP problem. This NP problem that we discussed, NP problem stands for non-deterministic polynomial time. Okay, non-deterministic polynomial type, and this has 2 different properties. NP complete problem means they have 2 properties. One is it should be verifiable in polynomial time. If you start measuring the time taken to approach a solution in polynomial time, okay, so given solution should be very quickly verifiable. That is one assumption, one property of these problems. Second thing is NP hard. NP hard means if you can solve the problem quickly, okay, one problem quickly, then you can solve all of them quickly. Okay, that is what the NP hard problem means. For example, traveling salesman problem. It's a classical problem wherein which you have to find out what is the optimal path, shortest path to travel between 7 to 8 cities or even more cities, n number of cities. Okay, this is used in airplane routing. Okay, so all these problems. So we have to find the shortest path. The problem is if you can find what is the shortest path traversable between the cities, then essentially you have solved that problem. So we call it as a polynomial time problem. Okay, NP hard problem. Okay, that is what NP complete means, and decision tree falls into that. Okay, falls into that arena, wherein which if you use NP complete, if you use a decision tree to get the optimal decision tree on the data, by given data, okay, because we are using greedy algorithms, it may not give us the global optimum. It may yes, at best we may get is local optimum. So that is another problem for this. Okay, that is we are just explaining here. We are only learning what NP problem means and what is greedy algorithm means. Okay, greedy algorithm means these are the algorithms just like your Hessian matrix. Okay, these are the algorithms that are tasked to find the optimum depth in the curvature. Okay, so greedy algorithm means it will look at your cost function and it will look at what is the cost function value at which I can see the least amount of what is the slope at which I can see the minimum or least amount of loss function or cost function value. That is what greedy algorithm does. Basically it goes on to look for local optimum, okay, in hope of finding global optimum. It aims for global optimum but may find local optimum. Okay, so that is greedy algorithm. And one example is coin change problem. Coin change problem means, okay, to make the change with fewest number of coins. Let's just say you have 100 rupees. What is the least amount of coins I can carry that will equate to the sum of 100 rupees? Clearly the answer is 10 rupees coins. 10 rupees coins will give you 100 rupees, right? That is the maximum coin available with us. So such problem, okay, fall under this greedy algorithm problem. I've given simple example for us. It's very straightforward to tell. Okay, but using algorithm to calculate, we have to arrive at the global optimum. Okay, so that falls under greedy algorithms. So these are the two types of problems that we have. Optimization problems, we call it optimization problems. Okay, one is NP hard, another one is greedy algorithm, just so that you know. Okay, because we are gonna reuse these in the concepts. Okay, several key concepts are there. One is the tree structure itself. Okay, each the point at which the data is split is called as a node, and there are three types of nodes. Root node is the topmost node. Internal node is the node at which splits happen, decision is made. Okay, internal node or decision node, they are the one and the same. Leaf node are the terminal nodes. Terminal nodes are the nodes at which you can see the output value. Okay, so this is leaf node. And next is splitting criteria. Again, we have not discussed Gini impurity in depth. I will talk about it, but for now, just understand there are splitting criterias. This could also be very potentially a interview question. They may ask you to list out what are the problem, what are the scenario, what are the different types of splitting criteria. One is entropy. Entropy you already understood. It's nothing but the measure of disorder or uncertainty or randomness in the data points. Nothing but multiple data points might be present. Okay, so that is entropy you already saw. And reduction in entropy, by partitioning we say that is called as information gain. If entropy reduces, information gain will increase. Like that, we also have something called variance reduction. A variance reduction is if you are using the decision tree for regression tasks, we instead of looking at how much amount of data points are there, now there you can't see data points. So you can't classify data points because those data points are not classifiable. They are rather floating values, right? Those floating values you can only calculate the certain metric like mean, median, standard deviation. You can't calculate the standard deviation or mean or median on classification target values, but rather on continuous values. Hence, decision tree uses another technique called variance reduction for regression tasks. How much to split, where to split is calculated based on the variance, not based on the entropy. Entropy you are counting what type of what data point belongs to which class, but there you can't count. It's a floating value. Okay, how will you count the floating value? So that's why we calculate the variance. What is the variance of this type of structure? What is the variance of this type of data points belonging to one class? So that way we'll do. So that is another criteria. Another criteria is Gini entropy. Gini or Gini entropy. So you are free to pronounce however you like. Okay. Another one is Gini entropy. So in Gini entropy, what you do is you try to measure the impurity and reduce it. It is mainly used for classification tasks. Entropy is used for classification tasks, information classification task, information gain, and variance reduction is used for regression tasks. Okay, so these are the things. Now, decision tree is based on multiple algorithms. ID3 iterative dichotomizer. Okay, it uses information gain as a splitting criteria. ID3 uses information gain, and decision tree is also based on C4.5. So these are the very classical algorithms that statisticians came up with. So C4.5 is extension of ID3, which can handle both categorical and continuous data using the gain ratio for splitting. And this is the next iteration of these C4.5, CART they call it, right? Classification and regression trees. So they can handle both. And actually CART is the latest version of decision trees. Okay, so they use Gini entropy and variance reduction. Gini entropy for classification, variance reduction for regression tasks. Okay, these are the various older versions of decision trees. Now pruning technique, what we have said is in pruning, see what is pruning in general time. Let's just say you are a gardener, you have a garden, you have a plant that is widespread. Plant, I'm not talking about tree, plant. So you have a plant, you have widespread, What will you do? You will take a scissor and keep on chopping off, right, its sides that have overgrown, to make it align in the certain direction, or to contain its extra growth, right? So you will keep on chopping off. That is what pruning means. Pruning means you will stop the tree growing beyond certain depth. Either you will specify the depth at which you want the tree. Okay, that is one way. That is called as pre-pruning. Pre-pruning means you will already tell the model even before the model runs how much depth you want. Okay, by default it is 10, by the way. And post-pruning means you will allow the tree to grow, but then you will remove the branches which have least importance, or nothing but you will remove the decision nodes which did not give you the proper classification. That is called as post-pruning. How we will do that? That we will see when we talk about parameters and how to control pruning and what are the steps taken. That we will see, but you understand the concept here. Next is feature importance. Now this is one of the out of the box property of these decision trees and random forest and XGBoost. What happens is you can measure the importance which decisions gave you the better tree. That can be measured. Okay, at each node, at each decision node, whatever the splits happen, so those can be measured, and that will tell you which are the important features that gave you the best results. Okay, that we will see. We have to plot this feature importance in one of our solutions, then you will understand. Okay, next is handling overfitting. Overfitting, how will you handle overfitting? What happens is decision trees, if there are noises present, they'll start learning the noise also. Okay, to prevent easily the to prevent the overfitting, we have to do these 3 steps. Pruning we have to enable, and this setting the minimum samples per leaf. Okay, we have to limit the growth of the tree. Again, setting the max depth. So setting the minimum samples per leaf as well as setting the maximum depth of the tree. Or we can use bagging. Bagging is called as bootstrap aggregating. This we will discuss how it works and all. Random forest you can use, and then boosting methods also you can use, like ADA boost, gradient boosting, XGBoost. So all these are boosting algorithms. Okay, in bagging algorithm, for bagging, random forest is a good example. So it combines multiple decision trees, trains on different subsets, and the idea is to reduce the variance and improve the stability. So that is what bagging means. Aggregating, bootstrap, these, if you learn the meaning of these two, you will understand what bagging means. Okay, aggregating means you will aggregate the results in the end. Okay, either using voting process or using calculating the actual weighted mean or mean. Okay, so for random forest does that. It does both for classification and regression task. Boosting means you will build the trees sequentially until the error in the trees is reduced. All these algorithms do the same thing. ADA boost, gradient boosting machines, and then XGBoost. Okay, GBMs we call it, right? GBMs. So those also will do it. We'll learn. Next is handling missing trees. So decision tree by nature they can handle the missing values, but if you have a way to use the if you want to handle the decision trees missing values by yourself to get better results, that is also a possibility. Okay, you can do that. Alright, so up until this point, have you understood some of the concepts that we need in order to proceed? Okay, good. So there is a good tutorial here. Okay, there is a good tutorial here. I want you to just have a look at it by Normalized Nerd. So he will explain how decision trees work. Nothing but the same explanation that we have gone through, but if you visualize it, you will get better idea. So that is what I'm trying to say. So I have attached this link. You please go through. Okay. Next is step-by-step process. This we saw pictorially. Now we will see how it works in the backend. So you have data set. Okay, you have split the data into 80% and 20%. Now out of that 80% of the data, okay, root node takes the entire data set. Okay, very important. Okay, so root node takes the entire 80% of the data set, and it will determine the best way to split. Nothing but for each row of data, cumulatively it will calculate what is the entropy, what is the information gain that it can achieve if it goes with certain splitting. And this is done for all the rows of the data. And once you have that calculations, so Gini impurity, it will measure the impurity in the data set. Impurity means the mixture of various data points. Okay, and the goal is to choose a feature that will result in the least amount of mixture of data points belonging to various classes. Okay, entropy and information gain can also be used, which measure the amount of randomness. Okay, information gain will reduce the entropy. So either one of these two splitting criteria can be used to come up with the splitting on that 80% data set. Once you determine, okay, so before that, how are they calculated? Gini impurity for classification is used. How is it calculated? It is calculated by, again, it is also calculating the probability only, probability of occurrence of a data point, okay, belonging to certain class. That is calculating. It is squaring it and summing it up from 1 to number of rows, and then it is subtracting from 1. That is the difference. Okay, but the common term is both are working on the probability only. Gini impurity also calculating the probability, entropy is also calculating the probability. Okay, so once you have the split basis on these criterion, you can divide the data set into subsets. How many subsets? 2 subsets. Each subset will form a branch. Okay, and again at each branch, that is at each decision node that you have created, you will again repeat the same process. Again you will go through, calculate the probability of occurrence of that particular data point, okay, and subtract it from 1 to calculate the Gini, and again you will do the splitting, and that will continue. This process will continue for all the decision nodes until a stopping criterion is met. And what is the stopping criterion? One of these 3. 1, maximum depth that you have specified, or 2, minimum samples per node that you have specified, and 3, homogeneous nodes, that nothing but pure splits have been achieved. Okay, it will stop splitting the nodes when all the samples belong to the same class. Nothing but pure splits have happened. Okay, so one of these 3 are the stopping criteria. Next is, once the stopping criterion are met, okay, now the model has to decide whether to assign, how to assign the label. See, you have done the splitting, okay, but you still don't know what class to assign it to. That is the question, right? I mean, that is the whole problem. How it will assign is, it will look at the majority. If it's solving a classification problem, it will look at the majority of the data points here. For example, here or here maybe. So here you have a mixture of these data points, right? It has split this data into 2 separate classes. Here you have obtained the pure split, but here you don't have the pure split. Here 1, 2, 3, 4, 5, 6. Okay, 4, 5, 6, 7. Here 7 data points are brown and 6 data points are apple. Now majority voting is done in order to classify these data points. Although they are misclassified data points, it will still go ahead and say these belong to cherry tree because brown is cherry. Okay, and these belong to apple. Okay, here because it has, okay, anyway, this is a decision tree, we can't talk about this one. This is a leaf node. Here you can see this green point, it belongs to apple and brown is cherry, but still it will go ahead and say this green point as cherry because all others are cherry. Same thing happens here. These 2 data points will be classified as oak. I know they are misclassified, but still that's how it will classify. So that is what is happening at leaf nodes. Once the stopping criterion are met, it will assign a label for classification or value for regression based on majority voting or average calculations. Okay. Now pruning is additional technique that helps in reduction of overfitting. So I would say we don't do pruning in the very first attempt. Run the model as is, then observe if there is overfitting. Nothing but you have to look at the training error versus test error. Training error, if it should be same as testing error, both should be minimum. Or look at the training accuracy, look at the testing accuracy. Training accuracy should be high and testing accuracy should also be high. If training accuracy is high, testing accuracy is low, clearly the model is overfitting. If the model is overfitting, then in the next iteration you have to apply this pruning technique. Nothing but you have to remove the branches that provide very little predictive power. Okay. So pre-pruning you can do using maximum depth, minimum samples per node. Okay, and post pruning is you basically allow the tree to grow as much as it wants, and then you remove the decision nodes that didn't give you the proper results. Delete the decision nodes. Okay, and again you don't have to do anything extra, you just have to enable one option and the model will do that for you. Okay, post pruning. Next is, once you have all these classified attempts, then you are making the prediction. Now this is where you are going to take the 20% of the data. Again you will start at the root node, you will pass all those values to already tree structure is generated. Right? Tree structure is already generated at let's just say at the decision point the value of diameter was 0.45. In the test data also it will pass the same test data to the same branch it has generated, same structure it has generated. First rule it will apply is 0.45 greater than or equal to 0.45 diameter. All those points will automatically be taken as oak tree. Okay, so it will use the same structure it has generated in the training data set to predict on the test data set. Okay, based on the rules it has come up with. Okay, finally you will evaluate the model. Evaluation metrics remain the same for classification and regression. For classification you have accuracy, precision, recall F1. For regression you have mean squared error, root mean squared error, etc., etc. And then you can also go on to visualize the decision tree. A function is already provided for you that will provide how the split happened. Clear? All the points are very same as what we discussed already. Is this clear? Give me a thumbs up, please. Okay, all right. Thank you. So next is, we are gonna take a sample value, sample data frame, and understand how it is calculating entropy. Okay. So how it is calculating entropy, how it is doing the classification. So very simple. Look at these labels. Labels are important for us to make the decision. Okay. Fruit, not fruit, not fruit. So if it is not, it's not a fruit if it is yellow and small. If it's not a fruit if it's yellow and large. Very clearly with your human intuition you can tell that color is playing the major role here. If it's yellow it's not a fruit. If it's red it's a fruit, because size is varying here. Size is varying whereas color is not varying. Okay, clearly just by looking at it you can say colors are playing the major role. Anyway, we will see how decision tree does this. So it will calculate the initial entropy on all the data set. What is entropy now? Entropy is nothing but probability of that particular value of all the values. Okay. So you have 2 fruits and 2 non-fruits. So entropy of the entire data set S is given by, see how many are fruits? 2 are fruits. 2 divided by how many are not fruits? How many of values are provided? 4. 2 by 4 into log 2 of 2 by 4, same value, plus how many are not fruits? That is 2 by 4. 2 by 4 log 2 of 2 by 4. Okay, very simple, right? So how many are fruits versus how many are not fruits? 2 by 4, and then if you do the sum, complete sum, it is 1. So entropy is 100% in the very first split. Okay, now it starts calculating the information gain. How much information gain can it happen at that particular entropy? So for color, now it has to decide which feature it has to take up in order to make the decision. So now it's going to look at the feature level. For color feature, how many are reds? 2 are red, 2 are yellow. If you take 2 are red versus the label, how many reds are resulting in the fruit? 2. Okay, so hence entropy is 2. If you plug in this equation 2 by 2 into log 2 by 2 plus 2 by 2 into log 2 by 2, log 2 by 2 is 1, log 1 is 0, this becomes 0, again first term becomes 0, 0 plus 0 is 0, hence entropy becomes 0. If you take color, entropy becomes 0, and that math is given here. So information gain is 1, because you have to subtract entropy from 1 to get information. So information gain, yes, if you take color is 1 minus 0 is 1. Understood? Next is for size. It's gonna look at size. For small, there are 2 samples. 2 smalls are there. This is one small, this is another small. One is fruit, one is not fruit. Okay. Next, 2 samples are there. One is fruit, one not fruit. Entropy is again 1. If you calculate, plug it in this equation, 2 divided by 4, how many smalls are used? 2 smalls are used. How many fruits are there? 2 fruits are there. See, this is, sorry, 1 fruit is there, 1 not fruit is there. So all values become 2 by 4. How many smalls? 2 smalls. How many total values? 4 values. 2 by 4. Hence it becomes 1. Entropy becomes 1. Okay, entropy becomes 1 for both small and large values. Now information gain is 1 minus 1 is 0. Entropy is 1, no? So 1 minus 1 is 0. Or you can calculate separately also like this. Okay, 1 minus entropy we have calculated. Entropy itself is giving us 1. 1 minus 1 is 0. Now clearly, if you use color as a feature for splitting, then the information gain is 1, highest information gain. If you use size as the feature to calculate the entropy, it is 0. Information gain is 0, entropy is 1. Clearly, you will make the decision based on the color. That's what is happening. You're gonna use the color as the option to make the split. Color, if it is red, it is fruit. If it is yellow, it is not fruit. So here, size is not used as the factor to make the decision tree. Is this understood? Okay, excellent. So this is how decision tree works. If you have understood this, then you have understood decision tree, random forest, XG boost, gradient boosting machines, light GBM. So all are algorithm 7, 8, 9, 10. You would easily understand 7, 8, 9, 10 if you understood this. Okay, anyway, moving on. So for you, although theoretically there are a lot of concepts you have to learn, but practically if you want to code, there is not much for you to do. For example, you will take the data, you will load the data, you will do some feature pre-processing. Okay, if you want to have better results. If not, you can ignore that. Then you will do the splitting. Make sure to set this random value. You can choose whatever random value you want. So random value you will choose. Then you will call the decision tree classifier, and which is present in sklearn.tree. In sklearn.tree you have lot of things. Okay, so you can download that. Anyway, so you will call that function. You will set max depth. You will if you want, you can set up minimum sample per node. Okay, and then you will fit the data. You will call the prediction. You will calculate the prediction scores. You will print the scores. You will plot. What are you exactly plotting? You are plotting the confusion matrix only. Okay, you are taking the confusion matrix. You are plotting it to understand, to just the clear view of the numbers, how many classified, how many misclassified. And then you also have another feature called feature importances. So if you call that classifier, in classifier only you have another feature called feature importance. It will tell you which features have contributed for the decision making very well. In this case, color. Okay, I mean for above one. For iris, we will see what it is. Okay, whether it is sepal length or sepal width, petal length, petal width, we will see. So then you can visualize. Okay, here you are plotting the decision boundaries for each one of those. Okay, so that is what. Let's look at the result. Accuracy, everything is 1. everything is correctly classified, 0 or misclassified, that's why everything seems to be 1 here. Okay, and if you, as you can see, we have 3 classes, so you have 3 particular boxes here, 3 different checker boxes. So confusion matrix is saying 19 are correctly classified as setosa, 13 are correctly classified as versicolor, and 13 are classified as virginica. And if you notice the feature importance, petal length is the determining factor. Sepal width is not contributing, sepal length is not contributing. Petal length and petal width are contributing factors. So how the split has happened? So at each level, you can see Gini has been calculated. The first petal length it has decided is 2.45. And how did it decide? Very, very simple. It looked at the entropy. It looked at the entropy as well as the information gain, or it calculated the Gini in this case. In this case, the splitting criteria was Gini. By default, it is Gini and Gini impurity. So basis on that, it has calculated, and it has also given you the class as well as the values. 105 samples it took initially, and then it split. Okay, so 31 came here, 37 came here. Okay, so basis on this, it has made this classification decision tree. Okay, and you can see because you at each split you are making a decision wherein which you are taking multiple data points under one particular decision. That's why you have a step piecewise. We call it piecewise function. That's why you don't have a curve or smooth decision boundary, but rather you have a decision boundary that cuts at 90 degrees. Okay, that's why we call it as piecewise. Okay, here also, as you can see, it's a straight line, but it's not curve here also. So different values are used to make basically what we are visualizing here is how it split the data at first level. This is what it is. At second level, how it split the data. Okay, at third level, how it split the data. Fourth level, so fifth level. Okay, so for 6 different things are used, 6 different leaf nodes are used to come up with this boundary. Now you can see the final boundary. This is how it has separated. Although there are misclassification, 2 data points are misclassified here, but because majority voting was there, it has applied those triangles into. It has taken in that way. Okay, clear? If it's all good, I want to stop here.